Just waiting on a confirmation. All right, let's go ahead and get started. Welcome everyone. Thanks for tuning in. I hope everyone is doing well and staying safe out there. My name is Yash Savani. I work at Reality Engines. Today evening, we're gonna be giving a workshop on unsupervised learning and deep learning based forecasting. So I'll start off by giving a talk for about 20 minutes on anomaly detection. Then I'll hand it off to Sam, who will give a short talk on deep learning based forecasting. After that, Austin will show you how to build your very own deep learning based forecasting model using our service at RealityEngines.AI. Finally, I'll be back to show you how to create an anomaly detection model using our service. At the end, Austin will make a few closing remarks and talk a little more about Reality Engines. So, okay, let's get started. I will start by talking about anomaly detection. Anomaly detection is a very important field in applied machine learning because in the real world, data is never perfect, and it's important to identify where the imperfections are. All right, sorry. It looks like there's a little bit of echo. Let me go ahead and fix that. I think the echo is coming from my phone. Okay. Hope that's a little better. Sorry. Okay. Let me go ahead and just go through that once again. I think there was a little bit of an echo there. Welcome everyone. Thanks for tuning in. I hope everyone is doing well and staying safe out there. I'm Yash Savani. I work at Reality Engines. Today evening, we're going to give a workshop on unsupervised learning and deep learning based forecasting. I'll start off by giving around a 20-minute talk on anomaly detection. Then we'll hand it off to Sam, who will give a short talk on deep learning based forecasting. After that, Austin will show you how to build your very own deep learning based forecasting model using our service at RealityEngines.AI. Finally, I'll be back to show you how to create your very own deep learning detection model, anomaly detection model using our service. And then at the end, Austin will be making a few closing remarks and talking a little bit more about Reality Engines. Okay, I'll start off by talking about anomaly detection. Anomaly detection is a very important field in applied machine learning because in the real world, data is never perfect, and it's important to identify where the imperfections are. Let's begin by discussing what an anomaly is. From a young age, we have an intuitive idea of what an anomaly looks like. If I have 3 apples and 1 orange, it should be pretty clear that the orange is the anomaly. Armed with this intuitive idea, we define an anomaly as a pattern in the data that does not conform to a well-defined notion of normal behavior. There are 2 key assumptions that all anomalies have to adhere to. The first is that they have features that differ significantly from normal features. This is the essence of what it is to be an anomaly. The more similar the anomalous point is to the normal data, the harder it is to classify. And second, anomalies are rare. If they were not rare, then we could use classical supervised learning techniques to identify the hyperplane separating the anomalous points from the normal ones. However, if anomalies are rare, we cannot use supervised learning as shown in the diagram since it's not clear where that hyperplane should lie. Note that whether you have enough labeled data points to train a supervised learning algorithm is dependent on the dimensionality of the data, but this is a subtle point and we'll come back to this a little bit later. Next, let's consider the different types of anomalies that exist. We classify anomalies into 3 categories. The first is a point anomaly. Point anomalies are anomalies that deviate significantly from normal behavior. They are usually easiest to identify. The second is a contextual anomaly, as are anomalies, and they're anomalies that are only anomalous when considered in the context of other data points. The third anomaly is the collective anomaly, And these are anomalies where multiple correlated features produce anomalous points simultaneously. By themselves, these anomalies might not be classified as anomalous, but since the behavior has changed across multiple features, they're considered anomalous. There are many applications of anomaly detection. Here I've listed a few. Some of the key ones we have been exploring at Reality Engines are fraud detection / intrusion detection. Here we try to identify fraud or intrusion based on anomalous user behavior in the data logs. The second is time series monitoring. Here we try and identify anomalous time slices in a time series setting. In the final part of this workshop, we'll be using the Reality Engine service to create our own time series anomaly detector to identify anomalous cloud spend. There is a general pattern to all anomaly detection algorithms. This pattern can be broken into 4 steps. First, we have to collect enough data to train the anomaly detection model with. Second, we analyze the data through some dimensionality reduction techniques. This can be like PCA, t-SNE, UMAP, your most famous dimensionality reduction techniques. This will be useful later on when we try to evaluate our model. Third, we fit the model to the data. There's a vast corpus of models we can fit to this task. However, the models I'm sure you're all most excited about are the deep anomaly detection models, and we'll be exploring one of these soon. Finally, we go ahead and evaluate the model that we've trained by giving both anomalous and normal data points to the model and seeing whether they are labeled correctly. This is where the results from step 2 can come in useful, as we can see which points don't fall in the borders of the dimensionality reduced visualization. Okay, so assuming that we've already collected and analyzed some data, we now want to train a model that can classify the anomalies in our data. While there are several models we can use, there are 2 key benefits to using a deep learning model. First, we do not need to do much data curation, since the model will automatically identify the best features to use. Secondly, the deep learning is especially well suited for high dimensional data, complex data with a lot of samples. Most practical use cases of machine learning fall into this category. Most of the deep anomaly detection models are based on conditional generative models like VAEs or GANs. The current literature has focused more towards the use of VAEs, though there are some papers that describe anomaly detection using GANs. But since there's more evidence supporting anomaly detection using VAEs, that's what we'll pursue to create our anomaly detector. A VAE is a deep learning model that is separated into 2 parts, an encoder and a decoder. So this would be the encoder and this is the decoder. The encoder takes in a data point, which is represented here by the green triangle, and encodes the data point into a location vector and a scale vector. An intermediary point or an intermediary step samples a new vector from a probability distribution with a location vector as the mean and the scale vector as the log variance. The decoder then takes this new sample and tries to recreate the input data point. In order to train a VAE, we use something called an elbow loss that includes a reconstruction error term, which scores how closely the reconstructed point resembles the original one, and a KL divergence regularization term that makes sure that the location and scale vectors do not deviate too far from a unit normal distribution. That was a whirlwind tour of the VAE, and I've omitted a lot of details. And I would encourage you to use the links in the bibliography below to learn more about how these models work. Forging forward though, to use a VAE for anomaly detection, we will first train a model on normal or non-anomalous points. That is, in this example here, we'll train an anomaly VAE to try and recreate the green triangles on the left as yellow triangles on the right. And then during the evaluation phase, we'll provide new data points to the VAE and attempt to recreate them. We measure how good our recreation is using a reconstruction loss or reconstruction error. If the reconstruction error is high, we can classify the data point as an anomaly. In this example here, the VAE is accurately able to recreate the triangle since it has been trained on triangles. It has been trained to try and create triangles. However, when we give the VAE a circle, it fails to create an accurate representation of the circle and therefore incurs a high recreation error. The intuition here is that the VAE knows how to recreate points from the normal data really well. That is, it has been trained, that is what it has been trained to do. However, if it sees a data point that is very different from the normal data points, it does not know how to recreate it. Therefore, it'll do very badly when trying to recreate the anomalous point, and we can use this badness as a measure for how far away the data point is from the normal data. Now that you have a sense of how to build an anomaly detection model, it is also important to be aware of the kind of data you are trying to train the anomaly detection model on. This awareness will help you make your models more effective. While this is true for any machine learning problem, it is especially true for anomaly detection because this is an unsupervised learning task, and the tighter the model fit, the less likely that anomalies can slip through. Some things to keep in mind when building an anomaly detection model are: what kind of data do you have? If it is sequential, you may want to use an RNN to encode your data. If it's an image, you may want to use a CNN. Another point to keep in mind is what is the dimension of your data and how complex are the interactions. If your data is very high dimensional and complex, then perhaps you need to use a very deep neural network with NAS to optimize the architecture. Finally, if you do have labeled data points you can train on, how many labeled data points do you have? If you have lots, you could try to use a supervised learning algorithm to train the model on. If you have none, then the deep anomaly detection model I described might be a better fit. If you have some, then you could try to use some hybrid meta model. Note, however, that if your data is high dimensional and has a lot of complex interactions, because of the curse of dimensionality, you'll need an exponentially high amount of labeled data to train a supervised learning model. You may find that training an unsupervised learning anomaly detection model will give you a better result in this case, even if you do have access to labeled data. So this is all well and good conceptually, but I'm sure my hand-drawn illustrations have left something to be desired. So we'll go ahead and jump into some code, and hopefully that'll be a little bit more convincing for you guys. So here we have a data set. This is a synthetic data set. It's a 3-dimensional S-curve that we'll use as our data. Any data point that appears on the S-curve or close to the S-curve is considered normal. Any point that's far away from the S-curve is considered anomalous. So yeah, here, take a look at the screen. A picture is worth 1,000 words here. As you can see, the data lies somewhat along the S-curve, and we're going to try and identify points, anomalous points based on this data. Admittedly, this is a toy example, but hopefully it'll help you understand the underlying idea. We then train a VAE to compress the data from 3 dimensions to 1 dimension. So the curve lies on a 1-dimensional manifold, so we should be able to do that relatively easily using a deep learning model. Note that PCA would not be able to do this because PCA is linear and this curve has extensive nonlinearity. So PCA can do a pretty reasonable job of dimensionality reduction to 2 dimensions, and this is a visualization of the results from PCA. So we go ahead and we're going to go ahead and train our VAE to try and recreate points, the 3D points from this S-curve data set. Note that the VAE is really simple. It's just the encoder is just made of 2 fully connected layers, and the decoder is another 2 fully connected layers. So it's a relatively simple deep learning model. It takes in 3 dimensions and it encodes it into 7 dimensions, and the encoding scale and the scale and the mean and log variance vectors are both one dimension. So this tries to compress it into one dimensional manifold, which should be very easy for the deep learning model to do. So we go ahead and we train this using an ADAM optimizer and use the elbow loss function as we described in the presentation, and we go ahead and we train it for 1,000 epochs. I've already gone ahead and trained it, so we don't have to wait for that. And we're going to go and evaluate it now. So to evaluate this, the anomaly detection algorithm, we're going to use a 3D grid. So here we have a 3D grid where each point on the grid represents a point that we want to evaluate the anomaly VAE on. So we'll go ahead and for every point in this grid, we're gonna try and recreate this point using the VAE. What we would like to see is that points that are along the S-curve have a low reconstruction error, while the points that are far away from that underlying S-curve have a high reconstruction error. So if we go ahead and we take a look at the results here, what we have here are the points that are the closest to the, as we slide through the slider, we see the points that have the lowest reconstruction error, and as we drag out, we get points that are further and further away from that are further and further away from the S-curve, which gives us a sense for how this VAE would have worked in practice. So the VAE is accurately able to reconstruct points along the center of this S, which is the data points that it was trained on, and the points that are further away get a lower reconstruction error. Get a higher reconstruction error and therefore a higher anomaly score. Okay, while this is a very toy problem, I hope it illustrates the underlying idea behind how most contemporary anomaly detection is done. In the final part of this workshop, we'll use the ideas I presented here to build a real-world anomaly detection algorithm that can be used to identify anomalies in cloud spend. In conclusion, anomaly detection is an important area of machine learning because often we may need to identify if a point differs from normal without having access to large amounts of labeled anomalous data. There are many techniques that have been used to help identify anomalous points. The one we have described today uses a VAE model, where we train the VAE to recreate normal data points and then evaluate the reconstruction error on the test data points to see how anomalous they are. Thank you for listening. Now I'll hand it over to my colleague Sam to tell you about deep learning for forecasting.
All right. Can people see and hear me okay? Am I streaming? All right, so I just have a quick presentation about deep learning for forecasting. So I'm going to just describe the outline of this brief talk is I'm going to formalize the problem of forecasting, talk about metrics for evaluating different algorithms on forecasting problems, and describe one commonly used classical algorithm, ARIMA, and then talk about the basics of how a deep learning approach works. So fundamentally, what is forecasting? So we have a time series, so a sequence of numerical values, and we either want to predict the next single value or the next k values for this time series. That's the univariate forecasting problem. And we also have a multivariate forecasting problem, which is parallel time series. So an example of this is you can think of, maybe I have many different electric meters, and they each have different readings at different intervals. So you can see in the lower right here, these may be different time series, but related and in parallel. So in the multivariate problem, we want to predict the next k values for each of these several time series. And another aspect of this problem is we may have, in the multivariate case, we may have different static features, so non-time dependent features. So you can think of an example of that is maybe I have information about the location of each of these meters, like maybe coordinates for each of them, and that may affect the shape of these time series. So that's something to keep in mind, is that we may have non-time dependent features in addition to time dependent features. So what are some challenges with this problem? One is that time series may or may not have a trend. So in practice, we may observe like exponentially increasing time series or oscillating time series, which are stationary in the sense of remaining in the same range. In the multivariate case, there may be many complex correlations that we have to try to exploit without overfitting. So an example of a situation like that is financial data such as stock prices, in which case there are many very complex correlations. And finally, there may be periodicity at different scales. So we may have weekly, monthly, yearly periodicity, and this may be weak or strong. In the example here, these are carbon dioxide readings. So you can see there's like very strong periodicity, very strong annual periodicity, and there's also an upward trend. So how do we, what are the relevant metrics for forecasting type problems? There are two that are widely used. One is called NRMSE, which is, so these like may look like complicated acronyms, but they're actually like relatively simple ideas. NRMSE is just the standard error divided by the average value. So you want to normalize the standard error by dividing it by like the average magnitude of values that you expect to see. The other commonly used one is called SMAPE, or symmetric mean absolute percentage error. And this is like an L1 norm. So we take the average of the absolute value errors, but we divide them by the average of the predicted and observed value. So the reason that we have this average in the denominator is for numerical stability reasons, but you can think of these as just like being the analog of L2 and L1 losses, like a squared error and absolute error type of losses. And they're complementary metrics in the sense that they give you complementary information, so you want to use both of them. So for example, if you want to penalize large errors more heavily, then you might use NRMSE, which is like an L2 loss, and vice versa. So I'm just going to quickly describe one classical approach to forecasting called REMA. So you can think of this as like being built up from a few different building blocks. The first is an autoregressive model, which is for your forecast at time t, you fit a regression to the previous p values. And then you can, there's a variant of this called autoregression with moving average, or ARMA, in which we add a time series of noise terms, and we introduce those to our regression. And this makes the model what's called weakly stochastic, because these noise terms are undetermined, and it's a method for reducing variance. So the number of noise terms you allow is Q, and the number of previous terms you use for your autoregression is P. So these are parameters you can vary to make your model more or less complex. And finally, ARMA assumes that your time series is stationary, meaning it doesn't have a trend up or down. So if that's not true of your time series, you can apply the differencing operator several times. Differencing means that you just replace yt by yt minus yt minus 1. And if you apply that several times, your series should be approximately stationary. So if you apply differencing d times and then use ARMA PQ, that's called ARIMA with parameters PTQ. And that's like a super common technique for forecasting. Yeah, so how does the deep learning approach work? So fundamentally, we use an RNN. If you're familiar with deep learning at all, your sequence of values get fed into an RNN, and then on top of that, we have a fully connected layer, and then this predicts the next k values. And we train this with backprop, as usual in deep learning. So what's the point of this, or why would you want to use this over something like ARIMA? ARMA is a linear model, so ARIMA is, you can think of as like a variant of a linear model. And if you have like complex nonlinearities, especially if there's relevant information which may be like very separated in time from like the time when you're predicting, that's something that deep learning can capture that linear models can't. And also, if you have like static features or other features that are relevant, because like neural networks are flexible, and you can put in additional features and concatenate layers and build them up from building blocks. It's easy to incorporate other relevant information. Whereas like for something like ARIMA, if you have static features like the location of an electric meter, it's not clear how to incorporate that. But in practice, like our architectures can be deeper and more complex than this like basic schematic picture. You can add like additional RNN layers, additional fully connected layers, but that's just like a sketch of the idea. Cool. So yeah, that's all I have. That's just an overview of forecasting and deep learning for forecasting.
All right. Thank you, Sam and Yash. Appreciated those in-depth talks, and I'm going to be switching gears a little bit here. So just to introduce myself, I'm Austin. I'm senior software engineer here at Reality Engines, and today I'm going to take you through a workbook and how to create a deep learning model, or a deep learning forecasting model using the Reality Engines service. So what you're going to do first, pull out your computers or just follow along with the stream. But if you're going to follow along on your computer and uh, create a Reality Engines account, all you have to do is join in on the link here in the on the screen. Also, it's in the description of the video. It is bit.ly/capital R, capital E, forecasting, all lowercase. Now, this is going to take you to this website. It is essentially, or it is a Google workbook. And essentially, Google Workbook is a cloud machine donated by Google. It allows you to run an entire Python environment. Gives you a little bit of compute, a little bit of RAM, a little bit of storage, and so that allows us to run through these workbooks, which and I'll show you how to use the Reality Engines Python API directly on this machine without you having to install anything, without you having to figure out how to run Python. So this is a very useful tool for demoing. So while you're navigating to this site, basically what we're going to be doing today, we're going to be taking the popular Rossmann store sales dataset, and something you can find on Kaggle, which is a machine learning website that provides a lot of datasets and competitions. So what this dataset contains is it's a bunch of time series data about different stores and their sales performance over time. And what we're going to do today is we're going to go and build a forecasting model to predict in the future how each store is going to perform. So I'm going to walk everyone through step by step here. I'm going to make sure it goes at an easy pace. If you're falling behind, feel free to reach out. We have a YouTube live stream chat. We have a bunch of people online to help out and answer any questions directly in live chat. Otherwise, they can reach directly to me, and so I can address any issues you might have and show you anything. So yeah, just please use the live stream chat for any issues. And yeah, so now hopefully everyone's navigated to this site. The first thing that we're going to do is create a RealityEngines.AI account. So we are a private beta. So it is you're going to be one of the first groups of people joining in on this website. So you do need to use this special link that I have inside of this workbook to create your account. This link I'm going to go ahead and click on that link now. And so that should bring me to this page. So it's a start your free trial page. It has the special token, which allows you to create your Reality Engines account. And so what I'm going to do here is just go ahead and fill in my information. I'm going to add my name, my email, and a password. Thank you, Safari. All right, and so once I've finished creating my login details, I'm going to hit sign up. And now the first thing that is going to prompt me is going to ask me to create an organization. So in Reality Engines, the highest level concept that we have is an organization. This is essentially just a container for your projects, your data sets, where all of your models, and you can invite people to join this organization and collaborate and help you maintain and create new deep learning models. So I'm going to create a new organization called Austin Corp. I'm going to create that organization. And then I'm going to get a new screen. It's going to prompt me on the top to say to verify my email. You should have at this point received an email to your email address with a verification code. We don't have to worry about that for this very moment, so we can verify that at a later time. What we're going to jump straight to is actually go ahead and create an API key. And so that's going to be the only thing we're going to do on the Reality Engines dashboard today. Everything from here on out is going to be through the Reality Engines API. So we're going to stay pretty close to the code. But we do need an API key to be able to interface with the Reality Engines website. So what I just did here is I clicked on that API key link and then created create API key. And you can feel free to give it a tag. This will just give it a little user-friendly tag so you know where you used your API key. I did not give it one, so you can either highlight that or just hit copy, and that will copy the API key to your clipboard. So I'm going to give a moment here. So again, just on the project, or on the entry page, splash page, you can click on and create an API key, and then go ahead and create your first API key, copy it, and then we're going to hop over straight back to the workbook. So let me go ahead and switch back to that tab. All right. So to get things going inside of this workbook, all you have to do to run the code, you do need to log in with your Google account. I did forget to mention that. So you must be logged in the browser with your Google account. If you don't have one, it's pretty quick to sign up. It doesn't cost anything to run these, but once you are signed in, you're going to go ahead and start hitting play. And so you don't need to do any typing. You will have to paste your API key in just a couple steps. But everything else should just be pretty point and click. I'm going to go through step by step and talk through exactly what we're going to do at each step. If you're falling behind, don't worry. It should be pretty easy to catch up. And feel free to follow along on on the live stream as well. So I'm going to go ahead and hit play on this first item, and that's going to give me a prompt. It's going to ask, or say that Austin at RealityEngines.AI created this notebook. You're just going to go ahead and click on Run Anyway. And so that's going to go ahead and provision a cloud computer for you. And so once you're connected, it's going to go ahead and download the Reality Engines Python API library. And so now that that's installed, we're going to go ahead and install two standard Python tools. One of them is called Pandas, and we're just going to use this tool to preview some of the CSV files that we'll be using for training. And then also PrettyPrint, it's just a useful tool for formatting the output and makes it a little bit easier to read as we go through the notebook. So I'm going to hit play on that to import those. And so now that those are all set up, here is where you're going to need your API key. And again, we left a little link here. So if you lost it from your clipboard already, just go ahead and click on this link. They'll bring you directly back to your Reality Engines dashboard. And you can go ahead and pick up your API key again. And again, if you are a little bit behind and need to create your account, make sure to click on the sign up link here. This is a special sign up link to get early access to our platform. So go ahead and create your account through that link, and then paste your API key in this prompt box. Before you hit play, if you hit play, it will assign an empty string to your API key. Don't worry, you can go ahead and hit play again, and that will overwrite the value and set it to your correct API key. So once that is set, the next step is to import the Reality Engines client and instantiate it with your API key. And so if this doesn't give any output, then we have a authenticated client and we are ready to go. So I'd already explained that we have organizations, and organizations are your team and house all of your projects. Well, a project inside of Reality Engines is a container which contains all of your data sets and your models and deployments. And so these are going to be very specific to your business use case. So Reality Engines uses business use cases to tailor your deep learning or our deep learning algorithms to produce a better performing model than say just using or just using a generic AutoML search. So we're going to actually, Reality Engines has built out a whole library of use cases to address specific business needs. And so we can go ahead and see what those use cases are by clicking on this next API call. So this will list the use cases that are currently available. So it's a pretty big list. It has a bunch of descriptions here, which you can read up on at a later time. You can also check it out on our website. It's a little bit easier to consume that way. However, we are going to go ahead and select retail as our use case of choice for our project tonight. So as I mentioned earlier, because we are trying to predict retail, or we have a retail data set, and we're trying to predict future sales for those stores. So I'm going to go ahead and hit play on this next box, and that will set my use case to be retail. And now each of these, or for each use case, the project requirements are going to be a bit different. So for this use case, we're going to have specific requirements for the data sets that you're going to be uploading and what values need to be inside of those data sets in order for us to train a model. So for this use case, retail, we have a few required columns. We have a date column, which is just a timestamp of each of your or each of the rows for your store history. We have demand. So this is a numerical value representing the value that you're trying to forecast. So it could be the number of customers that have come into your store or the number of items that you sold at any specific time. Finally, we have some optional items. We have a future. So this is a known value ahead of time that we can use to help the forecasting algorithm predict a more accurate value. This could be, say, a holiday. So we're able to accurately guess that whether it's a Black Friday holiday, we can predict that our sales are going to be through the roof, or a day that we have off that our sales are going to be zero. So this is just useful information that we're going to know ahead of time. And so we can, and so like state holidays, school holidays will be useful for helping us, or helping the algorithm predict better for those special cases. We have an ignore column, so if we had some extra data in our CSV that we just didn't want incorporated, we can tag it with ignore. And then finally, the item ID. And so that's going to be say, a store ID or a specific product that we're trying to forecast. It'll be the unique identifier that we'll use to track it throughout all the timestamps in the history. The second data set, which is optional that we can upload, is just extra auxiliary data for our items. So we had the item inside of the time series, which like the product ID or the store, and this data set is just going to be extra information. Perhaps it's the zip code where the store is, or maybe it's some item attributes like the price. Just any information that's that's going to be constant throughout time for a forecasting data set. And now, finally, we can actually go ahead and use the API to create the project. So we're going to call client.createProject. We're going to give it the name of store sales forecasting, and we're going to give it our retail use case. And so when I hit play here, it will give me a new project ID, which I'll be using throughout this workbook. So now that we've created our project, the next thing we have to do is upload those data sets to meet those requirements in order to start training our model. So Reality Engines is really flexible when it comes to how you're providing your data. We provide in data warehouse, so you can go ahead and upload directly to Reality Engines and through a CSV on our website through our API. You can also connect your AWS S3 buckets or Google Cloud Storage, and we can read the data directly from those buckets without having to import. Or we can also use publicly available data sets, which we'll be using today. And so we have a S3 bucket that we don't even need to connect. It's publicly available data on our S3 bucket. So all that we're going to do is we're going to take a quick look or quick peek at the data using pandas. And so the first thing that we're going to do here is click on this next box. So for the sales history data set, we'll download the data set here on the machine, and we'll take a quick peek at what's inside. So this data set has 844,000 rows. The columns we have the store, so that's the store ID. The date is going to be our timestamp. The sales, the number of customers, whether or not it's a state holiday and school holiday. And then the second data set we'll be using is the store attributes. So the first column here is going to be the store number or the store ID. And so that matches with the column in the first data set. And we have a grand total of, let's see, about 1,114 rows. We have a little bit of metadata about our store. So we have the store type, assortment, competition distance, and so just a little extra data that we can give to the deep learning system, and it can use that information to help better predict the forecasting time series. So now that we've previewed the data, we're going to go ahead and upload or point Reality Engines to where these data sets exist. So this is a public S3 bucket, which allows us to just directly import read the data directly from these buckets. So when I hit play here, it's going to create two data sets, the store sales history, and I have the pointer to the sales time series. I'm going to give it my project ID, and I'm going to give it the dataset type time series. So I'm just telling it what kind of data is inside of it. And the second data set that I have here is the store attributes. I'm going to give it that location as well as the project D, and I'm going to give it the dataset type item attributes. And again, these special types here, the dataset types, you could find by calling the get requirements above. So the describe use case requirements has the dataset type time series and the dataset type item attributes. All right, so now that we've pointed Reality Engines to these datasets, Reality Engines is going to go and read through these datasets, and it's going to go and featureize and do a lot of processing on the data. So what's going to happen now is that Reality Engines is processing. I'm going to go through a for loop and just check on each of the datasets and get the status. So the first dataset is done processing. So the Reality Engines detected the schema already for this dataset. So you see for each of the columns, we have a schema object. It's got the name of the column, the mapping that we detected, as well as the data type. So it detected that store was the item ID, and it's the identifier. We got the date as the column mapping date, and it's the timestamp. Sales, that's what we're trying to predict, our demand. And then we have a couple more columns which it didn't have any extra mappings for, but we do have a state holiday and school holiday, and so these weren't detected to be future. We don't try to overpredict that because we don't know what you're going to have in the future, but in this case we do want to tell the system that these are values that it can expect to have when it's predicting the future. So what we're going to go ahead and do is go ahead and tag these two columns to be column mapping future. So I'm going to first just show you again, these are the valid column mappings, the description for each. And so the next step is just to set the column mapping. So I'm going to call column.setColumnMapping, or client.setColumnMapping. I'm going to give it the project ID. I'm going to give it the dataset ID. Then the column that I want to set the column mapping for, and then the mapping that I'm giving it. And so in this case, I'm giving it future for both state holiday and school holiday. And so after this is done, it will give out the schema that we have, or the resolve schema now. And so I now have both future columns properly mapped. All right. So quick whirlwind through getting our project set up, but now we have all the requirements that we need in order to actually train a model inside of Reality Engines. If we wanted to check through the API to make sure that we do indeed have everything, we can call on the project object, we can call .validate, and that's going to return a project validation object. It's going to give me a valid true. If I did have errors, for example, if we weren't able to detect an item ID and I hadn't yet set it inside of my data set, it would tell me what columns I were missing. But for this time, we got everything correct, and we're not missing any of the required data sets, so we should be good to train. So before we start training, there are a bunch of options for actually training our model. So Reality Engines does a lot of work to tune these parameters to get you the best performing model possible. But it is something where we do give people who have a ML background the ability to tune these parameters to really be able to fine tune exactly what you're looking for. The one training config option that I do want to point out, which is impactful for everyday, is the prediction length. So the training config option prediction length is going to dictate how many steps into the future we're going to predict. So let's say that we have a daily entry for each of the stores and how many items it sold for each day. If we gave it a prediction length of 7, it would predict 7 days into the future. If we wanted to predict 30 days into the future, we would give it a value of 30, and then it would predict 30 days into the future. So if we wanted to change this up and try out some different training config options, all we have to do inside of this is forecasting project.trainModel. We have this training config parameter, and so all we have to do is give a map value of prediction length and the value of how many days into the future we want to predict. So if I wanted to predict 30 days in the future, I'd set it at the 30. And then when I train this model, it's going to produce a model that predicts 30 steps into the future. For this workshop, I'm going to go ahead and leave it as the default, but I do encourage you to come back and experiment and play around with these. And you can also, of course, toggle all of these values inside of the Reality Engines website as well. So I'm going to go ahead and hit train model, and so that kicked off a training job inside of Reality Engines. So it's given me a model ID as well as instance. I've got my store sales forecasting model, and we should be good to go. So this training will take approximately an hour to an hour and a half. So we're obviously not going to wait for this to be completely trained here in this workshop, but you will get an email as soon as your model is done training. So I do encourage you to come back and continue on. I provided a checkpoint, which I'll show off in just a moment. But while your model is training, I did provide a deployment or a model that I've already pre-trained for you here. And so you can make a call with the get forecast API on my model, and we can go ahead and predict and see what the output will look like when your model is done training. So if we hit play on this cell. All right, so here we have a map with three keys. It's P10, P50, and P90, and those are different quantiles for the forecast. And then we have a list of 7 objects, so we had a prediction length of 7. by default. And so we have the date in the future, or this is going to be the first timestamp in the future that we're predicting. And then we have the sales, and that's going to be the number, or the predicted number of sales for that time step. And so we'll have 7 for each of these. If we had changed the probability quantiles in the training config, we could also turn on other quantiles. So we have the P10, P25, P50, P75, and P90. By default, we only do the 10, 50, 90. And so this next call here will block on waiting for your model to complete training and also evaluating getting metrics. So you can go ahead and click that if you want and wait for that to complete, and then you can just follow along on my screen, and I'm going to show you a quick I'm going to resume in mine on a checkpoint and be able to actually show you what you can do on the model once it's done training. So I'm going to go ahead and switch to a new tab here. And so when your model is done training, sometimes these machines on Google Colab will actually time out, and so you'll quote unquote lose your progress. But don't worry, you can resume fairly easily. So all you have to do is open this checkpoint section, and so what this is going to do is once you enter your API key, you can go ahead and hit play. You'll get prompted again to run anyways, and what it's going to do is going to resume where you were. So it's going to fetch your projects. It's going to find the project that you're working on. It'll get your model, and then it will get the model, make sure it's done training. And so it'll get you right back where you were, and so you can go ahead and continue with your workbook. And so you can see on the last line here, we have our forecasting model, and the status is complete. So it is done training. All right, so once we're done training, the next step is just to figure out how did we do. So we can get the model metrics directly through the API, and so this is going to spit out quite a bit of information here. But the most important information is the, as Sam had covered in his talk, the normalized root mean square error, and the symmetric mean absolute percent error. So we have some little definitions for each of these. But then inside of our object here, let me just go ahead and scroll down to the bottom. We do have the score for NRMSE and SMAPE. So we're able to get a score of 18%, which is less than our 30% target. And for our SMAPE, we got 23%, which again is a pretty good score for our forecasting. And so this basically what happened was we took all of the training data, or all the data that we were given, we split it into training data as well as some evaluation data, and we used the evaluation data to test to see how our prediction, our forecasting algorithm actually did. So we took off some data and predicted the values, and then checked how close we were to the actual values that were in the data set. And so we had a pretty good model for this data set. And again, if you want to go in depth later on, you can go ahead and read more about all of these values inside of the model metrics. And you can use these metrics to compare across reality engines. If you try to train different models using different parameters, you can see how each of them compared, and see which method and which parameters actually gave you the best method, or best performance for your data set. And you can also compare against other services as well to see that Reality Engines does really well. And so once you're actually happy with your model performance, the next thing to do is to deploy the model. And so this deploying the model essentially just reserves some cloud infrastructure to host your model, and that way you can make real-time and batch predictions against your model, and then actually produce some results. So what we're going to do here is just click play on forecast deployment. It's going to create the deployment on this model object. So what it's, as I said, it's just reserving some cloud infrastructure to host the model. And once we're done creating this deployment, we'll be able to make the predictions that I had shown you above. So essentially what we do is we create a deployment token. And so these deployment tokens are different from our API keys. Our API keys allow you to use all of the API calls that you've seen in this workbook, as well as managing your models, deployments, creating new projects, and inviting new users. We obviously don't want to embed all of that functionality inside of anything or anywhere we want to use Reality Engines. We want to use Reality Engines everywhere for our even perhaps on customer dashboards, etc. So what we're going to do is create a deployment token which will authenticate just the prediction calls. And so in the above example, when I had made the prediction, I was actually using a unauthenticated client, but I provided the deployment token, which then authenticated my request to make these predictions. And so now this is safer to embed inside of a client-facing website, app, or even inside of your own infrastructure. And so now that we have a deployment token and deployment, we can call the same thing that we did above, this time with get forecast with our deployment token and our deployment ID, as well as the query data for the first store. If we wanted to change up the store, we can enter in any other store ID and give me a different time series. This is great for getting predictions on one store at a time. But if you wanted to actually create a batch prediction, and so say you wanted to get forecasted data for all of your stores inside of your data set, what we can do is call a batch prediction job. And so this will allow, or this prediction, or I'm sorry, this API call will create a batch prediction job, which will take your entire data set. It will take each store and predict for every time series or every store in your data set the next 7 or whatever your prediction length you defined was number of days into the future. And so this is obviously a much longer process because we have over 1,000 stores that we need to predict for. But this allows us to not have to sit and go through each of our stores, hit predict, save that value, but we'll actually produce just one file with all of the predictions that we can then download and embed in our sales reports or to present to our CEO. So this will obviously take just a moment as it's got a lot of stores to go through, but approximately for about a data set this size, it should take about 45 seconds to a minute. And then once this is done, Reality Engines allows us to define either an output, which is inside of one of our S3 or GCP buckets. Otherwise, if you don't provide any value, it'll save it inside of Reality Engines, and then we can, once it's done, it will give us a download link, and we can go ahead and view it directly inline using pandas. And so while this is spinning, this does get me to the end of my talk. So in just a moment, I'm going to hand back over to Yash to go through how to create a anomaly detection deep learning model using Reality Engines. And so you will find that link both at the top of the workbook as well as the bottom. And that will be bit.ly/R_E_anomaly. And you'll need your API key that you had created. We provide links in the other workbook as well to be able to grab that, and that's all you'll need to get going on the next workbook. And so I think with that, I'm just going to hand it off, as this batch prediction job has taken a little bit longer than expected. But at the end, if there's a little bit more time, I'll show the results for the batch prediction job. So with that, Yash, go ahead and take it away.
Okay. Thanks, Austin. So now that you've had some experience building your own forecasting model, I'm going to show you how to build your own anomaly detection model using the Reality Engines service. So if you go ahead and click the link in the forecasting notebook, it should take you to the anomaly detection notebook that you're seeing on screen right now. If you can't find the link, you can also go directly to this link, bit.ly/R E anomaly _anomaly. So it's bit.ly/E _anomaly, and that should take you to the same notebook. Cool. Yeah. So in this notebook, we'll be training an anomaly detection model on some realistic cloud spend data. So first, we're going to have to go through some setup, and this should be identical to the forecasting notebook. So as long as you followed whatever everything in the forecasting notebook, you should be ready to go with the anomaly detection workbook. So once again, just for those of you who may have come in a little bit later, you can sign up using this link here, and then you can get the API keys using this link here. So if I go ahead and take my API key, this is like I've already created one for my for this workbook and this project. I will be taking it down after this, so it is this one here, and we'll be using this to run this workbook. So like the forecasting use case, we're gonna go ahead and pip install Reality Engines, make sure that we have that set up in our environment, and once we have that ready, we'll go ahead and import some other tools that we'll need. Pandas to handle our data, prettyprint to print some of the JSON stuff, and then, like I said, go ahead and pick out your API key from the link. There's another link here if you have lost yours. So go ahead and just click the link. It'll take you to the API keys. You can create a new API key by clicking this button here, and then just make sure you copy and paste the API key. And yeah, once you have the API key, you should be able to go ahead and run the next few commands, and we should have a client set up. So this client will help us interface with the rest of the Reality Engines interface. Yeah. So we'll go ahead and this time we're going to have to create another project. So this time what we're going to use is the operations cloud. So the project here will be anomaly detection for cloud spend. So we'll have some cloud spend data, and we're going to try to find anomalies in that cloud spend data. And the use case for that is the operations_cloud. That's already been filled out for us in this workbook. But so we'll go ahead and run that and make sure and take a look at some of the requirements for this use case. So some of the requirements for this use. So there are two data sets that we're allowed to that we accept for this use case. The first one is the time series use case. So sorry, the time series data set. In the time series data set, we'll have a column for the date. We need a column for the date, a column for the service ID. So in our case, there'll be an Amazon RDS service and an Amazon EC2 service, and the column which identifies which service the row belongs to will be the service ID column, and then the value for the actual value itself. This is going to be the time series dataset type, and this corresponds to the historical time series data for the cloud spend, and we'll be using this to identify the anomalies within this dataset. The second dataset that we accept is an auxiliary dataset that is not time series dependent. So this may be any additional information you may have with regards to the services. So if you have other information about the type of services that you're running, like locations, where they may be loads, things like that don't change with time, that would go in this dataset. We're not going to be using this item attributes dataset, but that is available for you if you had additional data for your use case. Okay, so we'll go ahead and create a project called Cloud Spend, and as we see, it's just a Cloud Spend data set with the use case operations cloud. The next step is going to be to add some of these data sets to the project. So we have this time we're actually going to upload the data set. So if you go ahead and click this link here, you will see you will get a CSV that's downloadable, and that CSV is what we're going to use to train our anomaly detection model. So that CSV, that link here is the one right here, and we're going to go ahead and load that CSV and take a look at it here. So as we can see, this CSV includes 3 columns. The first one is a user start date, so this would correspond to the date column. It goes from 2019, January 1st, 2019, up to August approximately. Yeah, and there's a service, like I mentioned, there's the Amazon EC2 service and the Amazon RDS service. So each row corresponds to a specific time for a given service. So you see this is the January 1st EC2 row, and this is the January 1st RDS row. And we have the blended cost, which is the value that we want to identify anomalies for between for each of these. So we go ahead. So this is the data set we're gonna be trying to identify anomalies for. This is not very useful, sadly, to look at, and you can't really tell anything from here. So we can take a look at the plots, just a basic plots to see where we might want to identify anomalies. Again, going back to the first talk, this is the part where we visualize the data and try and see points that we would want to evaluate our model on later on. So as you can see, there looks to be like one obvious anomaly here in the RDS data set, which is right here. So as you can see, it kind of follows a similar pattern. There's some minor anomalies here, maybe another one here, but this one here seems to be a very significant one, and this might be something that we care about, and this might be the one that this is the one we're gonna evaluate our model on. There are some anomalies for the EC2 one too, so we can check them out too. So now that we've taken a look at the data and visualized it, we're going to upload this to the Reality Engines project that we created. So the next code block does that for us. So we get the confirmation that the CloudSpend dataset has been uploaded. This is the same cloudspend.csv dataset that we just downloaded. Next we're going to make sure that we map the schema from the CSV data to the required schema from the for the use case, so that the model has the correct fields available. So just to make sure that the schema is correct, we have the user start date, which is a timestamp, which is correct. The service, which is categorical. This makes sense. The service has two categories: Amazon RDS and Amazon EC2, and then blended cost, which is numerical, which is what we're going to identify the anomalies on. The next step is going to be doing the mapping, so doing the column mappings, and like we showed above, the date, service ID, and values will be mapped to the user start date, service, and blended cost respectively. So that's what we're going to do here. We're just going to set the column mapping for user start date to date, service to service ID, and blended cost to value. Cool. Once we go ahead and do that, we're ready to go ahead and train our model. So we're going to run we're just going to go ahead and check to make sure everything is ready to run the model, and we can see that the project validation is true. So we can go ahead. So we're ready to go ahead and train our model. So before we train our model, we see that we have a couple of training config options: the test split, the dropout rate, and the batch size. We're not going to worry about these right now, but later on, if you want to build a more powerful model or want to mess around with these, feel free to. There's a chance you might get like something better than what we find. So the next step is going to be to actually go ahead and train the model. And similar to the forecasting use case, in this step, we go ahead and run the train model. This will train, and it'll continue to train, and you'll see this pending. And when it's ready, you should get an email saying that the model has been trained, and then you can come back and go through the rest of this notebook for the rest of the notebook that's like relevant to the to your specific model. But I've already gone ahead and trained a model before this, so we're gonna go and take a look at what you would see once your model has been trained. So this is actually running one of the predict commands on the data set, on like the model. So this is like predicting the anomaly score for the model, and as you can see here, it returns a histogram. So the histogram basically gives us the values, the anomaly score values going from 0 to 100, where each row or each element of this list is a quantile. So this is the 0 percentile quantile, this is the 1% quantile, the 10% quantile, and it goes up to the 90th percentile quantile, and you can see the values for each one of those. Yeah, that's the histogram that's a histogram you'll get out once you've trained the model, and you'll also get based on the parameters that you give the data here, you'll get a list of items, and the items will include these anomaly scores, where you'll get the blended cost, the start date, which corresponds to the same usage start date and blended cost from the data set that we looked at above, and an anomaly score. So this anomaly score is the newly calculated anomaly score, which you can use to identify anomalies in the data set. So once you have that, we can so this gives us an indication of how this prediction code will look, or once you've trained the model, how it'll look. So after we started training the model, we can block using this block here. So if you just go ahead and click that, if you run this block, then the code will be blocked until the model is ready. If the notebook or Colab notebook closes, then you can refresh your notebook and restart from this point by just unhiding this and running this again. So if you run wait for evaluation, but the Colab notebook closes, then feel free to refresh the page, go ahead, scroll down to this point, unhide this piece of code, and run this with your API key, and you will be ready to move on without any changes. So the next thing is, once we have a model and once the model is trained, we'll be able to get the metrics for the model. So right now the model is not available because it's still being trained, but once it's being trained, you'll be able to see the metrics for the model, and maybe we'll take a look at that once the model has been trained a little bit later on. But once the model has been trained, you'll be able to get the metrics for the model, as well as deploy the model. So this is the same steps as the ones that Austin went through for forecasting. So the metrics here will give you the mean and some statistics about the anomaly score. This is an unsupervised learning task, so there are no accuracy metrics because there is no labeled data here. But what we get is essentially statistics about the anomaly score. So the mean anomaly score, the standard deviation of the anomaly scores, a sense for how distributed the anomaly is, and that might give us a sense for how well this model, how many anomalies this data set has. Again, we will come back to this a little bit later once the model is done training. So if we continue, and if once the model is done training, you'll be able to deploy the model, and in the next two steps, you'll get a deployment ID and a deployment token, and both of those will help you. Will be the parameters that you put in to this predict command. So this would be the deployment ID, and this would be where the deployment token goes. And once the model has been trained, you should be able to go ahead and copy those into these fields. Copy your deployment ID and deployment tokens into these fields, and run this cell, and it should work and give you the same results that I just showed you before. So while we're waiting for that model to train, we're gonna go and use the model that I've already trained for you guys and go and visualize what these results look like. So in this piece of code, we've gone ahead and taken a slice of the data set that's somewhere around here, and we're looking for the anomaly score in Amazon RDS across this time frame here, and we're trying to look for what the anomaly score looks like around this point, which we would like the anomaly score to be high for. So if you go ahead and look down, as you can see, this corresponds to the Amazon RDS. The Amazon RDS a service, and the blue points here, the blue line here corresponds to the actual blended cost, while the red line here corresponds to the anomaly score. And as you can see, the anomaly score is relatively low up until this point where it suddenly jumps up, and we can see there's a high anomaly score indicating a correct anomaly at this point. Note that this is a windowed operation, so the jump here corresponds to the point where the window is fully where there's a point here where there's a window here where the entire window is an anomaly. So what we have here is anomaly score that's relatively low, and then it jumps up and we get a high anomaly score, and then once the anomaly has passed, it goes back down to regular levels as expected. And again, this is you'll be able to do this with your own model once the model has finished training. All you'll have to do is change the deployment ID here and the deployment token here to correspond to the ones that you'll get after running these two cells when your model is trained. To make changes, you can actually change the window that you look at here. So the time series window that you look at here, you can change which slice of the data you're looking at by changing this command. So if you want to look a little bit earlier, you can take a look at what it looks like earlier, and the index corresponds to the service ID. So a service ID of 0 was RDS, but a service ID of 1 would be the EC2. But yeah, so doing that will let you scan through this data set to look for where the other anomalies might be. Okay, so this as you can see here, there are not that many anomalies. The score is pretty low. It's scaled here, so we can see 0.8, which is relatively low score as we'd expect for this window here. Okay, I think that is it. Let's go ahead and check to see if our model has completed training. I don't know if it has, but maybe we'll give it a little bit. Maybe we'll give it a little bit longer. But if it doesn't finish training within the next few minutes, then it should the steps should be identical. You should just be able to go ahead and wait for this to finish. It'll block. Once it's finished, you'll be able to get some metrics and deploy the model, and those will give you those will give you the deployment ID and deployment token that you'll need to run this last cell, so you can see the anomaly scores across the data set. But okay, it does look like this is taking a little bit longer, so maybe we'll okay, well, again, this is probably this part is identical to the stuff that in the forecasting notebook, so perhaps we'll skip this. You should have something ready very soon. This doesn't take very long to train. The data set's relatively small, so you should have something very soon. And yeah, so if you have any other questions, you can post it in the YouTube live stream, and I'll take a look and see if I can help you guys out with anything. Okay, that's all that I have for you for the anomaly detection workbook. I'll hand it off now to Austin, who will make some concluding remarks and talk to you a little bit more about Reality Engines as service. Cool. Thanks, guys.
All right. Thank you, Yash. So, and as Yash said, I'll just wrap a few things up. So I did want to show you the batch predictions did complete. So now when we read the value, we'll see that we did get a prediction for every single store. We'll have basically two columns. We have an input and then a prediction, and each of these the input is just the store ID, and the prediction is the same as the output as earlier for each of the stores. And so now that is complete, I'll just pop back over to the product. So at this point, if you did train the model around the same time I did, your project should be complete, and so you should be able to finish the rest of the steps. But I just want to show you real quick the Reality Engines product. So as I had mentioned earlier, or in the talk, everyone here has gotten a early access to the Reality Engines platform. So you can come on here, you can create more projects. We've got a wizard to help you pick the right use case. So we have plenty of use cases here. And it'll walk you through exactly what's needed for each data set. And we've got a lot more images and a lot more guides for actually helping you get started on your first project. But going back over to the forecasting dashboard, here you can see both of the data sets that you have in your project. You have the schema mapping for each of these data sets. If you wanted to change something, you can come over to the schema dashboard, and it will allow you to go ahead and change any of the items inside of the data set if you wanted to retrain. And also we have a lot of visualization tools for the data. And so once that is done loading, it will show like charts for the distribution of the data. And also the model metrics. So we have a little more visualization here too of the values over the data sets. And finally, the prediction dashboard. So once you have actually deployed your model and you can make real-time predictions, we'll actually pull up the history of a store. So you can see over time, here's the number of sales. Obviously, the store seems to be closed. Here's a holiday. And so you can see some of the predictions here. So let's say let's pick 1001 identifier. So this is the dark blue line is the actual value, and then we've got each of the quantiles. So we're able to map fairly well along the shape of the data. If we pull back in history a little bit, we can make predictions over a different window. So obviously very, very accurately predicting the weekends or on Sunday when the store is closed. We have a prediction, and of course you can change some of the quantiles if you didn't want to visualize those. We have the prediction API, so this will give you an example, exactly as you saw in the workbook, of how to actually run the forecast. You can make you can change and play around this data. So this is actually hitting the endpoint. So when you hit run, you'll actually get the real predictions formatted for you, and you can provide additional data here as well. And lastly, of course, we have the batch prediction dashboard. So this will allow you to make and manage your batch predictions jobs, and you can view all the results here on this dashboard. And so, yeah, I definitely encourage you to come back on, train new models. As I mentioned before, you can mess around with all the training parameters here. We have a bunch of advanced options too if you want to experiment and get really into the weeds of training a model. And also uploading your data sets, or even linking your cloud storage and importing them directly into the product. Super easy. It's all free for you to come on here, experiment. And so I definitely recommend you take advantage of it while we're in this early access stage of Reality Engines. So with that, I wanted to thank you all for joining along. It's been fun. I hope you've learned something and have something to take away. And please shoot me an email at austin@realityengines.ai if you have any questions or have any follow-ups. And I'll be happy to help. And so with that, thank you very much for joining, and I look forward to the next time.